All right, thank you. So this is committing to the bit, relational programming with semiring arrays and SAT solving. So I'm Dmitri, and we'll get going. All right, so the topic of our research is semiringKanren, which is a new variant of miniKanren. So I'll go over some of the differences and explain more what they mean and how they look like later. All right, so one of the core main differences is that as opposed to miniKanren's top-down evaluation, semiringKanren employs a bottom-up evaluation strategy more similar to data log. So similarly, miniKanren computes relations as functions on streams, sort of essentially. SemiringKanren computes arrays, multidimensional arrays as relations. miniKanren is dynamically typed usually with S expressions, but semiringKanren is statically typed using algebraic data types. miniKanren is usually unweighted, but semiringKanren is weighted, and we'll talk more about what this means. And where miniKanren is often a shallow embedding within scheme, for now semiringKanren is a deeper embedding. All right, so just a motivating example. Here's how you might implement a coin flip relation in miniKanren. So it's just either heads or tails. No real surprise there. So as I mentioned, in semiringKanren, we have algebraic data types. So we either have unit types, sum types, which are either left or right, product types, which are pairs. And so a Boolean could be defined as a sum of two unit types, as shown there. So a coin flip in semiringKanren looks a little different, but it's essentially the same thing under the hood. So we're either calling lefto on the coin variable or righto on the coin variable. So lefto and righto are they're sort of relational constructors for the left and right. They're the relational versions of the left and right constructors for some types. So note that we need to introduce a fresh unit variable. That's because the lefto relation has 3 arguments for the internal type, so we do need to pass in the internal unit variable, but besides that, it's pretty much the exact same thing as up here. All right. Do you want me to go back? Or?
Yeah, what's C?
C is the coin argument variable, yeah. All right, so as mentioned, another core feature of semiringKanren is weights. So we can use the factor goal to add weight to a branch of a program where the weight is drawn from a semiring. So quick reminder on semirings if you're not familiar with them, but they're essentially a set with addition and multiplication operations where multiplication distributes over addition. There's some other constraints, but that's what it boils down to. So for example, real numbers with multiplication and addition, obviously, or Booleans with or as addition and as multiplication. All right, so we can do a weighted coin flip. For each of the left and right cases, we can conjunction on factors. So here we have left occurring with weight 0.7 and right occurring with weight 0.3. Yeah. So semiringKanren supports recursion, as one would hope. So as an example, we'll do transitive closures or graphed connectivity. So we can represent a graph as a relation. So here we have 0 is connected to 1, and 1 is connected to 0. So you can see that it matches the graph. We can express connectivity with this connector relation. So either there's a direct connection between 2 nodes in the graph, or there's some intermediate node that connects the first and final node arguments. So if we evaluate this over the Boolean semiring, we just get connectivity. So 0, I guess I'll point. Okay, so 0 connects to 0, so we see a true there. So it connects to 0, but 0 connects to 3, it does not. So we see a false there, or a bottom. But if we use the min tropical semiring instead, we get the shortest path length. So we can see 0 to 0 has length 2, I guess assuming these edges have weight 2, which we do need to encode with a factor. sorry, weight 1 with a vector. Yes, okay, 0 connects to 0 with 2. 0 connects to 1 with 1, but 0 does not connect to 3, so we give it weight infinity, which is it's the the identity value for the minimum composition law. All right, so how does this end up working under the hood? So relations compute multidimensional arrays. Variables are specific dimensions of these arrays, and goals are operations on these arrays. So let's focus on the first two. So if one dimension of an array is a vector, so we need a way to represent values as one-dimensional arrays. So for example, I'll do this pair of Booleans value, and we'll see how that gets translated to an array, because it shows all of our different types. So pair left sol right sol is a prod of two sums of units. So sols just get compiled to the vector of a single element with the one element of the semiring. Left and right gets translated to direct sum of vectors. So we have our sol is 1, so we have our sol there, and it's being vector direct summed with a 0, which is the size of the other side of the type. We fill up a vector with the size of the other side of the type and add it on. And then pair is handled with Kronecker product of these vectors. So here's what all the encodings for the type look like. We can see that for each value of the type, we get a vector that has a 1 in one location and zeros in all the other locations. So values become one-hot vectors, and the size of the type corresponds to the size of the vector. But what if we have more than one vector more than one in the vector? As mentioned, relations compute n-dimensional arrays. So this can be seen as a relation where the pair of two lefts or pair of two rights succeed, because the one in the first entry corresponds to pair of two lefts, and the one in the last entry corresponds to pair of two rights. We've got both of them there. So it's a relation where they both succeed. All right, so relations compute arrays. Non-zero entries denote successes, and 0 entries denote failures. So what do relations look like on more than one variable? So as mentioned, variables are specific dimensions of these relation arrays. So if we have a relation over multiple Booleans, for example, then x and y each get a dimension of the relations array. And so you can see it's a 2x2 array, because each dimension corresponds to a Boolean, which has two values, then two Booleans, so two-dimensional array where each dimension has size 2. So if we, for example, consider the relation where x equals y, then we get what looks like a unit matrix where there's a 1 where x and y are both true, and a 1 where x and y are both false, and zeros in the other spots. Or if we have a relation where there's only a condition on one variable, we can see that, so we're doing true x, we can see in we only have ones when x is true, but we have ones in either slot for y. All right, so how do we use these relation arrays in practice? As mentioned, goals are operations on these relation arrays. So there are essentially two classes of goals to worry about. There's low-level relations. So like I mentioned, the constructors for the types we have, equality, disequality, which is pretty nice, succeed, fail, factor, and then applying relations, and then goal combinators, which are conjunction, disjunction, and fresh. So for low-level relations, we generate the array corresponding to that relation. So as mentioned, equality looks kind of like a identity matrix where we put ones in the places where they're equal. So implementing disequality is super easy. We just put zeros where they're equal and one where they're not. So that's very, very nice. Lefto and righto correspond to unifying the left and right parts of the array. So they correspond to unifying the left and right parts of the bigger variable with the smaller variable. It's kind of hard to show paro because it's a three argument relation, so there is a sort of third dimension. But it's a similar sort of thing where it goes into the structure of the variables and unifies the right parts with each other. And then factor just fills the entire array with the value. Succeed corresponds to factor 1, and fail is just factor 0. And then what relation application does is it unifies the arguments of the relation with the values of the variables in a pre-calculated relation array. So we'll explain what that means. We'll go into more detail about that later. So then there's goal combinators. Conjunction just corresponds to multiplication. So again, you'll remember for Booleans, and is the multiplication. So conjunction just generalizes that over any semiring. Disjunction is addition. Again, for Booleans, or is the semiring addition, so just following the same thing. And then fresh is summation over the variable axis. You can sort of think of it as a disjunction over all the values of the variable. Yeah. All right, so what about recursion? So we assume that the relations fail until we have more information about what they need. So as I mentioned before, when we call a relation, it uses a pre-calculated relation array, but in the case of recursion, we don't necessarily have that pre-calculated relation array. So we start by assuming it fails, just filling it with all zeros, and then we recompute. Once we have this initially version calculated of the array, we have some more information, so then we compute it again, and we repeat this process until there's no new information, so we calculate by fixed point, similar to data log. So going back to this transitive closure example, I'll do a step-by-step walkthrough of it. We start by the all zero case. So infinity is 0 for the min tropical semiring. So we start by assuming there's no connectivity. Then we fill in the information we have from the graph because we can already calculate that. So we have a 0 is connected to 1, for example, just based on the graph. So that shows up there, and so on. So then we can consider intermediate vertices. So we know 0 is connected to 1, and we know 0 is connected to 1, and 1 is connected to 0. So then we can add those together with the intermediate clause and put a 2 there, and we get the 2 there. Similar for the other entries. We reevaluate it, there's no new information, and we are all set for calculating this connecto. All right, so this is, again, bottom-up evaluation, similar to how data log does it. All right, the end. But what about committing to the bit? This presentation didn't really have any jokes. The joke is that there are no jokes. The joke is the meta-humor that the jokes is that there are no jokes isn't really that funny. The joke is that the meta-humor isn't that funny. The joke is that the meta-humor still isn't that funny. We have computed the joke by fixed point. All right, so compiling algebraic data types to bit strings. So when we're using bit strings, we don't get arbitrary sum types. We only have Booleans as our basic sum type. So the core idea is to take a left or right and compile it to a product of a Boolean and whichever of the subtype of left, not the subtype, the contained type within left or right is larger, and then we use Boolean as a tag for left or right. So assuming that the type for B or the type for Y is bigger here, we compile left to a pair of true and the internal part sort of projected into the type of the larger type, and right is just pair of false with its information packaged up. So the smaller type of the smaller contained type of the sum type needs to get coerced into the larger type. So for example, let's consider a nested sum type with 4 total values, so it's just a sum of 4 units, and this gets compiled to a prod of 3 Booleans. So working from the bottom up, right sol gets compiled to false. Wait, what's going on there? Okay, there we go. Right sol gets compiled to false, left sol gets compiled to true. So we have a special case for handling the left and right sol just because they're easy to map directly to Booleans. So again, sum unit unit gets compiled to bool. All right, one level up, the right gets compiled to a pair of false and false. So here, the right of left of sol gets compiled to a pair of false and true. Again, same sort of thing. But here's the interesting case. We have this left of sol, and down here, so sol is smaller than the bool type that we have as this orange part. So in the case we just have a sol, we compile it to true, or we fill the whole thing with trues when we need to coerce a sol type. So then one level up, the rights get compiled to falses, the left gets compiled to trues, the sol get compiles to just filling the whole smaller type with sols, and we're all done for compiling this type. So sum unit, sum unit, sum unit unit, the type we compiled has 4 values, but this product of 3 Boolean has 8 values, so we're not completely using the space efficiently. You could imagine just compiling it to 2 bools, which also has 4 values. But using this approach makes it a lot easier to adapt the semiringKanren code itself to use these compiled types. So again, assuming the type of A is less than the type of B. Right-O is the larger type, we'll remember. It just, so yeah, we need to compile only to true-O and false-O, plus the other things we have. So right-O gets compiled to a paro, which instructs, so paro, and we extract the tag, which corresponds to left or right in the subtype, and we just assert that the tag is false and unify the contained type. And then left-O is pretty much the same thing, except that we're testing for true, and we're using a coerced equals rather than a raw equals. So semiringKanren does generate type-safe code to do these, or it tries to generate type-safe code to do these coerced unifications, but then left-O and right-O just become true and false-O with this unification. All right, so note that, so again, it's inefficient in how it, I was trying to remember the point I was trying to make here. So because the compiled type does have more values than the smaller type, we also need to make sure it doesn't inhabit invalid values that fit into the type. So semiringKanren also generates code to make sure that this prod bool, bool, in practice only inhabits the 4 valid values that we want it to. All right, so once we've compiled the bit strings, it's easy to translate to a SAT problem. So true-O and false-O, just either give the Boolean variable directly or not. Unification is equality, and conjunction and disjunction, as we know, are and or. So this evaluates it over the Boolean semiring. So it does, it is more limited in that sense. But expressions that satisfy the Boolean semiring correspond to successes, and unsatisfying ones correspond to failures. So note, to do this, we do need to inline recursive calls to a finite depth. This does result in false negatives, but it should not result in any false positives. All right, so benchmarks. We did Sudoku as a benchmark, and the SAT solver approach is pretty performant compared to faster miniKanren, which on larger examples does time out. Note that the naive array representation, we end up getting arrays that are too big to hold in memory, much too big to hold in memory. So the naive approach doesn't work. That's something to work on. But the SAT solver does give us nice, pretty decent performance here. All right, so for future work, polymorphic relations. So right now, our relations are mostly restricted to the type, but it should be possible to make them polymorphic while only using one relation array per relation rather than generating a new relation array for each type. I guess sort of intuitively, we already kind of do this for equality and the primitive relations. So we just want to try to figure out how to get this to work for arbitrary relation arrays. And then once we have that, hopefully it should be more straightforward to get recursive types, which we currently do not support, but having them would obviously make the language a lot more useful. Potentially using an SMT solver to handle the recursive cases better and potentially handle non-Boolean semirings for when we're doing that kind of evaluation. Quantum computing annealing. So these relation arrays kind of intuitively look like superpositions of the argument variable values. And with relational programming, we get reversibility sort of for free just by swapping the orders of the arguments. So it kind of intuitively feels that this could potentially be a good, interesting paradigm for expressing quantum computations. But there's a lot of work to be done to see if it works out nicely or not. And then figuring out how different semirings behave in the system. I think it's possible to come up with semirings that do not converge over fixed point with this method. I think there's already existing literature in the data log sphere about what works and what doesn't, but just need to look into that some more. And yeah, just applications are always useful. All right, so I think that is about it with semiringKanren, committing to the bit, relational programming with semmering arrays and SAT solving. Any questions? And thank you.
I've often thought for a long time, like logic programming and array programming, this kind of temporal spatial duality in a way.
Yeah.
So like a lot of what you were talking about kind of reminds me of like APL.
Yeah.
And like array programming. I don't know if you have any comments on that or if that was inspiration or anything.
I guess I wasn't thinking too much about array programming in terms of sort of intrinsic connection. It's obviously implemented using array programming, and I was an array programming enthusiast at some point, so I don't know if maybe there's some subconscious connection there. But I can't think of any deeper connection beyond what I've shown here for now, but that doesn't necessarily mean there's not one there. Yeah.
Hi, so you're using just dense arrays to represent all the stuff on the dimensional. Have you thought about using a sparse representation? Because it seems like a dense representation is not going to scale up to like 32-bit integer variables or natural numbers.
Yeah, I agree 100%. We used a dense array here just for convenience of an initial implementation, but I definitely want to switch to using sparse arrays or, yeah, but I'm trying to think about other representations that aren't even necessarily arrays that could do the same sort of thing. Sounds good.
Hi, great talk.
Thank you.
You had shown an example earlier where you implement numbers. How are those translated to bitstring?
Yeah, so the, I think I'll just scroll all the way back. So the numbers are used for the graph to represent nodes in the graph. And those are just translated as sum types of a fixed size. So it's more of a notational convenience here than, I think I went too far. No, I didn't. It's more of a notational convenience just to keep it on one screen than anything else. Again, once we get recursive types and hopefully the nice one representation of an array one array representation per relation, we will hopefully get something fancier, but for now it's just a sum type under the hood. Yeah, finite sum type.
My first question is about if I compare with some other logic programming that solve the problem because it's pretty common in logic programming.
Yeah, so we haven't compared it to other logic programming languages outside the ones we showed. We did compare to a hand encoding of the SAT problem, and it is a lot less efficient of an encoding that we generate than a hand encoding of the SAT problem. But it does generalize nicely to pretty much any semiringKanren program, which is nice.
Also, there are logic programming that combine with SAT solving, which is called inter-SAT programming.
Yeah.
It works very well on recursion because it's essentially data
Okay, that's good to know. Yeah, we did read about answer set programming, and I think there's some extensions of miniKanren which incorporate answer set programming. I guess here we're kind of going for a different approach on it, but that's definitely good to be aware of, and it's on the radar, and it's something I'd like to look into more. But thank you.
All right, thank you everyone for your wonderful questions. Thank the speaker.